So, hello everyone, and thanks for coming over. I'm really sorry I'm not able to be in person at the conference, but it's a pretty intense time here at the RIT. Plus, we have a snowfall since 2 days ago. So, yay, new record in upstate New York, snow raining in the beginning of November. So, definitely, I encourage you to visit if you like plowing your yard and your driveway in November. But while I'm here to talk today, thank you so much for Roberto and Camille for the kind invitation. I kind of want to talk to you about continual learning, but from a little bit different perspective. So from the perspective of what we actually need to have in continual learning to make it truly adaptive. Because if you're going to look at basically at the history of adaptive machine learning, streaming machine learning, however you're going to call it, you're going to see there were two kind of a disjoint silos, two disjoint views on how we learn from streams, how we learn continually. One from data stream mining community and one from continual learning community, which again, as we know in the era of deep learning, many things have been, let's call it politely, rediscovered and without like kind of a look at what has been done in machine learning for past 20 years. So I'll try to give you like maybe an overview and show you that actually those two communities that do not work together a lot actually are the two sides of the same coin. And we need to have like a holistic hybrid view of this if we truly want to have a really adaptive, really continual learning system. So let me just Perfect. So basically, why do we even talk about continual learning? Why do we even talk about data stream mining, concept drift adaptation to changes? Well, the main reason here is that nowadays, and by nowadays I mean for over a past decade, we're no longer dealing with static data collections. So basically the good old days when you go to the UCI repository, any other repository, download a data set or a company will give you a data set. Hey, that's what we have, train your model, give us model. Those days are gone because where we live in dynamically changing, evolving landscape. New data is being generated continuously all over the time. Data evolves, properties of data change, new concepts emerge all the time. And we need to have tools that will be able to deal with this high-speed, massive flood of data. And this is connected, you probably heard the term data tombs. So situations when we are able to collect massive, vast amount of data, but we're not able to process them. And this is very often what happens with business, what happens in places like Amazon, etc. Once the data has been stored, it's very rarely revisited. So that is all why we need systems that are able to deal with this incoming streams of data in real time, that are able to adapt and basically evolve together with the new data arriving in real time. This is basically one of the graphs I've been using for over a decade in any kind of a talks. It's basically from a website, What Happens in Internet in a Minute. They update it obviously every year because it's the exponential rise of those numbers are pretty scary. So if you look at this, every 60 seconds on the internet traffic, we get around 20 million text messages being sent, around 220 million meetings conducted on Teams, 228 people downloading Zoom, 3,500,000 hours streamed of Netflix in a minute in internet. So we're dealing with insane flood of data. And basically, if we do not have machine learning systems that are able to harness this, well, we're falling behind. And this is what a lot of companies, a lot of, well, governments are catching up, realizing that if they want to be competitive, if they want to really uncover what's going on in the data, they need dedicated solutions that can, well, take advantage of the fact that new data is being produced so massively and so frequently. So for those of you who have been in machine learning for a while, you probably remember the explosion of big data, Hadoop, Spark, MapReduce, all of those catchy words. And basically, one of the good things that came from this little bit overhyped bubble, like most of the bubbles nowadays in data mining, machine learning, is the notions of V's, which of course started pretty nicely with the velocity, volume, variety, value, veracity, very important aspects of learning from massive collections of data. Where I always say stuff value is, in my opinion, the most important one, because we always need to remember we build machine learning systems for a reason. And in real world, it's not necessarily to get another CVPR or ICDM paper, it's to generate some value for the company. So we always need to have in the back of our heads that our view as academia and the view what industry wants, what governments wants, are not always perfectly aligned in the same sense, and there needs to be some concessions, mainly from our sides, if we want to attract funding opportunities and adapting to what Navy, government, companies may need. But when we talk about data streams, when we talk about continual learning, the two V's from this pie, the volume and velocity, are the ones that we're going to focus on. So basically, what is a data stream? So the most universal definition, in my opinion, of a data stream is basically an unordered, because they have timestamps, but potentially unbounded, infinite collection of instances that may arrive with time varying intensity. In most of the research papers, we just assume they arrive in blocks, chunks, or one by one. But in reality, if you think about this, data is going to arrive with varied size of chunks depending on the hour. If you look at ATM traffic, there's going to be massive ATM traffic in certain days, like in the evenings, in the rush hours, and there's going to be way less ATM traffic at 4 a.m. in most of the cities. With data streams comes the notion of the velocity. So the speed at which data is generated, the speed at which data arrives, and the speed at which the data needs to be processed and ingested by the machine learning system. But this also deals with the volume. So with the fact that we are not able to store all the instances coming from the stream and revisit them, which basically goes to requirements for one-pass learning, learning on the fly, zero-shot, one-shot learning, however you're going to call it, basically assuming we'll have limited opportunities or even no opportunities sometimes of revisiting the data that passed through our system. So basically, if you look at this, you're going to think, okay, so that's data streams or is this continual learning? Where does it fall? So basically, as I mentioned, if you look at the area of machine learning over the years, there's been multiple silos when people dealt with these aspects of machine learning, giving them each other names, different names. It's the same stuff like with imbalance. Then suddenly somebody revisits long tail recognition and pretends it's a different domain versus just imbalance with a lot of classes. The same thing happens with data streams, continual learning, etc. So basically, I like to look at this as various aspects of incremental learning scenarios. So basically, scenarios where the amount of data grows over time, new concepts have emerged over time, and we need to deal with this. So if you're going to look at this like a kind of a holistic taxonomy that we discussed for years, you're going to have problems such as task incremental. When we get big blocks of data, each block is a different task. Collection of classes, segmentation, NLP problem, etc. So we kind of need to give new capabilities to our machine learning system. Or we may have class incremental, when we discover new classes over time and they arrive to our system and we need to ingest them one by one. Or you may have data incremental scenarios, which is my favorite type, which is totally unbounded data stream. And it's completely up to you. You need to discover, is this old data that you know? Is this new data arriving? Are there some anomalies? Are there some adversarial cases? You don't get any guardrails in terms of class boundaries or task boundaries. You need to discover everything on your own. So if you look at the two main competitors to the fame among the domains that claim they're dealing with evolving adaptive data, you're going to get on one hand the community of data stream mining. So this is kind of a well-established community. If you're going to look at the first papers by Pedro Domingos of very fast adaptive decision trees, this is around 2000, 2001, you're going to see that this domain for the last 25 years have mainly focused on adaptation to changes. So the main goal in data stream mining is how to keep our model relevant to the current state of the stream, which is connected with a big challenge called concept drift. So the fact that your data are gonna evolve over time, class boundaries gonna change, class distribution is gonna change. So your system needs to be constantly updating itself to keep itself relevant to those changes. So this is what data stream mining is focusing on. On the other hand, around 2015, 2017, when deep learning started taking over, people realized, hey, we want to add new knowledge to our deep networks, but when we add new information, our network focuses only on the new stuff and completely forgets all the past information that has been stored there. So this is continual learning. Here, the main goal is incorporation of new knowledge and retention of the incorporated knowledge. So how to avoid a phenomenon known as catastrophic forgetting. So basically how to have good performance on new data without losing the performance on the old one. And if you look at this, They both deal with new information arriving to the system in keeping your system relevant, but data stream mining focuses on adaptation and continual learning focuses on retention. So two little bit different goals, but both actually needed in real world systems. And we'll get back to that a little bit later in the talk. But let's maybe first also focus on the very unique nature of evolving, adaptive, dynamic streaming data, continual data, because this is not as trivial as it may seem. Because when we talk about machine learning algorithms for data streams for continual learning, we need to be aware with specific limitations of the field, or specific, I would maybe say, requirements connected with that field. So we need to have algorithms that are capable of incremental processing. There's no retraining from the scratch. We need to be able to have the same backbone, the same algorithm that can be constantly updated with new information. But we also need to be aware of the fact that we are working under certain constraints, such as limited time. Incorporation of new data cannot take forever. The decision making cannot take forever. We work with limited memory. We cannot store entire stream. We cannot even store a high number of examples. And even if the memory, you may say, becomes cheaper and cheaper, you're going to have a lot of scenarios like edge devices, microprocessors, etc., when the access to memory is extremely limited even now. And on top of that, our data are going to change over time. Some known concepts gonna become outdated, some classes gonna emerge, some classes gonna disappear. So we need to have mechanisms that will be able to track those changes and adapt our model accordingly. So when we talk about evaluating data stream mining and basically streaming algorithms, we all know tons of good metrics, accuracy, G-mean, AUC, etc. But I wanted kind of a point out to you, there's a big family of metrics called frequential metrics. So frequential metrics have this very interesting decay factor added to them that downweights the performance of the model on all data. Because if you think about this, if you have a model that constantly gets better or constantly get worse, their average accuracy may be the same. But we don't capture, so any standard metric doesn't capture the dynamics of learning. It will not capture if your model is improving. It won't capture if your model is degenerating. So that's why we use frequential metrics that have time-based weight factor that's going to pay a little bit higher attention to the performance on the newer and newer data. So then you can draw conclusions. Where are we getting with our learning? But additionally, when we talk about any kind of a streaming continual methods, we also need to report stuff like memory consumptions, update time, and decision-making time. So let's look independently at data streams and continual learning to kind of understand their specific quirks in each of those domains. So when we talk about data streams, the biggest challenge I've been working over for years and years is concept drift. So changes in definition and distributions of the learned concepts and times. So you think about this, our personal interests evolve. At certain point in time, let's say in college, we're gonna be Googling what's the cheapest alcohol that we can buy in the local vicinity versus hopefully 10 years later, we're gonna be Googling about decent health insurance related to what we did 10 years earlier. So our interest is gonna change. When we have children, suddenly our interest changes. When we have certain health problems, our interests change. So we cannot assume the same interests gonna carry on throughout our lives. Language changes. Like one of the projects I did for Amazon was basically tracking the evolution of hate speech in Amazon reviews. So stuff like this changes dynamically. Certain terms that have been completely okay over the years, suddenly something happens in the geopolitical situation and those terms become derogatory and we need to capture them and adapt. So we cannot assume that once learned data always gonna become relevant. When we deal with sensors, this is like one of the things we're doing now with Navy, how to adapt to degradation of sensors over time, because sensors are expensive. You don't want to replace them the moment they start degrading. You kind of want to get the sweet spot that you still can get some data from them and replace them only when they become truly not reliable. So basically, when we talk about data streams, we are kind of connected with the terminology using time series, stationary and non-stationary time series. So stationary series is going to be a situation when the data is continuously generated from the same distribution. And basically what we're doing over time when we learn from stationary data streams is we discover this distribution. But that's not what's really interesting for us. For us, it's more interesting a situation when we have non-stationary data streams. So our distribution gonna evolve. And there's tons and tons of views and definition of concept drift over time. I basically like to focus on the speed of changes, which is very strongly connected with the velocity of data. So you may have sudden concept drift. So a situation when one concept is instantly replaced by the other. Imagine a situation when you have security cameras, one of the cameras gets destroyed, suddenly your data changes. You may have gradual changes when old concept starts appearing less and less frequently, and the new concept starts appearing more and more frequently. Like a situation when, for example, gas prices goes up and you start seeing less and less cars with the students on the campus and more people are biking and walking. Or you may have situations like incremental changes. So when you have kind of a intermediate step before the new concept solidifies. And this is a big challenge because those intermediate steps are not that interesting for us. And we need to distinguish, is this the new distribution or is the distribution still changing? And we shouldn't focus too much on adapting to it. Another view on concept drift that is also extremely important from the point of cost management when you talk about concept drift adaptation is the distinction between virtual and real concept drift. So virtual concept drift means there are some changes in data, like different sampling, different representation, that actually do not strongly affect the posterior probabilities, so the class boundaries. It's a situation when we learn what a car is. We never seen a violet car, but purple car appears. It is technically a novel data. It is technically a concept drift, but the machine learning algorithm that is learned to distinguish cars still gonna tell it's a car. So this is not a situation we should adapt to changes. And then we have real concept drift. Like for example, we learned people distinguishing people by there's eye color, etc. Suddenly everybody starts wearing eyeglasses, and the previously learned concept of facial detection no longer applies to the current state of the data, and we need to adapt to the new distribution. So real concept drift is the time when we want to pay the cost of adaptation. So how do we handle concept drift? So there's a couple of approaches. We can rebuild the model whenever there's something new. Terrible. Don't do this. We don't have money. We don't have time, computational power. So may either use detection of changes. So this is an external tool called concept drift detector that basically tells your model when the changes are significant enough to rebuild the model, or we use a embedded incremental machine learning algorithm that basically works in an online incremental mode and tries to track the changes and readapt its structure accordingly. So this is what's been main focus of data stream mining. Now, switching to the more recent younger brother, the continual learning. So in continual learning, basically the goal is learning a sequence of tasks, classes, whatever we're going to define. And each of those tasks going to contain a certain representation of data. So our goal is to learn each task incrementally without losing performance on the old task, so avoiding catastrophic forgetting, but also hopefully managing knowledge transfer. So leveraging the knowledge from the past tasks to achieve better adaptation to the new ones. Because over time, we're learning some basic underlying concepts, shapes, colors, etc. And we do not need to pay the cost of learning the same concepts over and over again. So ideally, we're gonna have this forward transfer that's gonna help our model adapt to new concepts over time. And the same assumption as in data streams, once we learn the concept, data stops being available and we need to move on. So when you look at the continual learning architecture, and I'm just going to give a very, very broad overview, the main problem is the lack of accessibility to the data. So there are multiple techniques based on regularization, representation learning, replay techniques, etc., that try to mitigate the issue of catastrophic forgetting. But the biggest challenge in continual learning is this part here, is the trade-off between the stability and plasticity of the models. And this is where the entire difficulty starts happening. So in continual learning, we have the catastrophic forgetting. If we start adding new data, our network gonna instantly forget, massively forget previous learned information. We need to have knowledge accumulation, so long-term memory for our networks. That's going to allow us to store 20, 40, 100, infinite number of tasks in the backbone. But also we need to have forward and backward transfer. Backward transfer is the most challenging part here because it's the assumption that learning new concepts actually going to make us perform better on the past information. Very challenging, not that well explored area in continual learning. So as I mentioned, in continual learning, biggest challenge, stability plasticity trade-off. When we have high plasticity of our deep learning neural network or any kind of a machine learning algorithm, we fastly, quickly adapt to new data, but we have a very high risk of overwriting the previous knowledge. The gradient updates, the learning rates are high, so we basically start forgetting very quickly. When we have high stability of our network, then we're very good at preserving the past knowledge, but we do not adapt to new information very well. So you can imagine that situation, we try to get a trade-off. How to have capabilities of extracting meaningful, generalizable information from new tasks while maintaining the performance on the old data. And in control learning scenarios, again, massive domain, basically flooding over the main conference in a couple of years. You have class incremental, task incremental, or even more interesting, domain incremental scenarios. Domain incremental, very fascinating area. Again, not explored as much as the others, but this is, for example, when we train on real images and then we move to hand-drawn images. And we want to have a neural network that can be able to recognize the same class among real photos, hand-drawn photos, 3D generated imagery, etc., etc. Very, very interesting. Used a lot in remote sensing. A lot of people in my center that deal with NASA things, etc., are using this to be able to recognize the same concepts across different modalities. So, in continual learning, we have this massive problem of catastrophic forgetting. So what is actually catastrophic forgetting? It's a situation when whenever we show new data to network, instantly we forget the old ones. The weights are overwritten, the gradient is updated, and we lose performance on the old ones. Why this happens? It's because when we learn any deep neural network, while we accumulate information coming from all the past tasks, we have access at any given moment only to data from the newer task. So the weights of the neural network are updated only based on the new batch of data. So that means for the current data, we can approximate the empirical risk, we can calculate the loss, but we cannot do it for the past data. So in that case, when all data is no longer available, where basically there's nothing reminding the network, hey, you had some other information that you learned from. Now you're just gonna try to basically be a greedy optimizer, which is all neural networks, what neural networks basically are, greedy optimizers, and maximize the gains from the loss on the current data. So that's why we have a lot of catastrophic forgetting mitigation techniques, experience replay, regularization, etc. And we focus on that, how to stop neural networks from forgetting. And the big thing with catastrophic forgetting, it's not a solved problem. We can mitigate it, but we're not going to solve it. And there's basically a lot of papers that do not get the catastrophic forgetting correctly. And for example, train one model per class, they don't update it and they say, hey, no forgetting. But the whole idea is to have a backbone that have all the concepts merged together. Because if you have separate models, there's no knowledge transfer. There's no forward, backward transfer. It's not actually continual learning. So if you think about what I just told you, we have those two siloed research areas. We have data stream mining people, we have continual learning people, not a lot of communication going on. I would say even they attend a little bit different venues, they publish in a little bit different journals. But if you look at this, the continual learning is basically stationary. It focuses on knowledge retention, tackle catastrophic forgetting, no techniques for dealing with changes in the data. Once the concept is learned, we just focus on preserving the concept. We do not monitor it. Has it changed? Has it evolved? In non-stationary data, in data stream mining, we focus on change adaptation. Whenever a change happens, we adapt. But did we just forget all in the past? We don't care that much. We always assume the current state of the stream is the most important one. So you think about this from a holistic perspective, obviously they're not bridged together. There is a lack of holistic solution. There's big dichotomy between those two domains. So if you think about this, a truly continual learning system should be able to adapt, incorporate new information, retain all the information that is still relevant. But when the information starts losing its relevance, a continual learning system should be able to start forgetting it in a good controlled way, because that's the way we can achieve adaptation to concept drift, by unlearning or basically guided forgetting of outdated concepts inside our neural networks. So basically, with two of my PhD students, we published like two papers that kind of starts tackling this domain, which is again a very early stage research in this, and this is more like a tip of on the iceberg. And what we recently sent to transactional machine learning research should get published hopefully in a couple of weeks, is a plugin for every existing experience replay technique for continual learning. And experience replay is a situation when you hold a small buffer of old instances to remind the neural network that there's been some old tasks that we've seen. So whenever we train on new tasks, we mix in this little bit of old instances from the buffer to remind the network and stop this uncontrolled gradient adaptation only to new data. So basically what we proposed is a very lightweight plugin that works with any type of those experience replace techniques and basically focuses on using a drift detector on monitoring the test set. When the test set changes, our stream starts giving us different representation of one of the tasks, one of the classes. We localize, is this a local change, so only one of the tasks is affected, or is this a global change? All data tasks are affected, and we start scoring instances. So instead of just flashing everything, replacing the memory with everything new, what we do instead is we look at each of the instance and try to adapt, like assess its, let's call it freshness. So how relevant it still is. And instead of replacing everything, we do a targeted replacement of only the most outdated instances, which basically allows us a very selective realignment and way more stable learning than just flashing the buffer and replacing everything. So we basically avoid collapsing into single solution because we still maintain coverage of all the classes, but we do this at very, very small, negligible almost computational cost. So the big thing in continual learning, obviously benchmarks. There are no benchmarks with concept drift. So one of the things we did is we actually procured a concept drift version of popular benchmarks, MNIST, Cypher 10, Cypher 100, Tiny ImageNet, and we injected concept drift over time into them. And the very interesting trick is, because we're dealing with deep learning, the concept drift not only affects classification, but it also affects feature representation. So our backbone also collapses over time, and the feature extract, as you can see, become less and less discriminative over time. So that's also additional source. The feature extraction becomes additional source of difficulty inside concept drift. So basically, we tried to do a couple of different ways of injecting concept drift in our data. Rotation, permutation, defocus, blur, which is very popular way dealing with lenses, etc. And basically from extensive experiments, turns out that the rotation and permutation are the most basically invasive types of concept drift. So we focused on them. So basically what happens here is we compared popular experience replay methods, dark experience replay plus, CLS experience replay, air experience replay, with and without our drift adaptation, where you can see the blue line is basically the behavior experience replay with no drift happen. So that's our upper bound on a stationary stream. The red line is how this method behaves when the data stream is injected with concept drift. So as you can see, we start losing performance pretty significantly over time. And then we have two baseline methods. FR is fully relearning. That means we flash all the buffer every time and just replace with all the new instances. AMR is our proposed selective realignment that flashes only selected outdated instances and not everything. So basically what is interesting, there's not a big difference between full relearning and our proposed AMR solution in terms of accuracy. Okay, so you may say, so why do you have those more advanced techniques? Why do you have those selection, scoring systems, etc., if the accuracy kind of starts converging to similar solutions? Well, the answer is in what I talked at the beginning, that in continual learning data streams, we do not focus only on accuracy, we need to focus on computational cost and time. So while our solution gives similar accuracies as just flashing the buffer and learning from the scratch, we do this at massive, massive lower computational costs. So we have, as you can see, managed the same accuracy at massively different sample cost, how much samples we need for relearning, how much time per epoch is required, and how many GFLOPs we get in those relearning regimes. And here, as you can see, this is the difference between the sample adaptation between AMR and full relearning. So with a buffer of 500 instances, we need 5,000 instances labeled for full relearning and only 125 for our method. And remember, those labels don't come for free. When we work with benchmarks, we don't think about this. But when you're going to give this to army, company, etc., they need to pay a labeler. They need to have access to labeled data. So they actually really, really care about situations, about algorithms that can deal with significantly reduced access to labeled data. And this is also like a radius plot where we put the time, sample required, and GFLOPS requirements for the full relearning and our method on top of each other. So you can see the basically massive scale difference in the costs, computational costs required by those methods. And the bigger the data set, the bigger the gains. Which you compare, like for example, Fashion MNIST versus Tiny ImageNet, you can see the gains by our methods are significantly increasing. So finally, this is, I mentioned, only like a tip of an iceberg, something when I like talking about as an opening a new direction for continual learning systems. But where to look next? Because we know we need to adapt. We need to have this balance of knowledge preservation, adaptation to changes. But what else? What to do to make those continual learning systems even more deployable in real world scenarios? So in my opinion, there's 5 main directions that should be taken by the research community. Adding adversarial robustness. So what happens when the concept drift is not a real concept drift, but is actually simulated? So somebody is attacking you with a fake examples and try to force adaptation of your model to fake data. Or on the other hand, somebody is attacking you with adversarial examples to cover the fact that data changes and force your algorithm to stay behind compared to competition. How to model slow changes. What we worked previously works very well when the change is sudden, but how to do modeling when the changes are very slow. How to deal with open set and subclass emergence. How to deal with situation when new classes may arrive over time. How to distinguish concept drift from new classes. And how to deal with situations when the modality of data in terms of distribution characteristic change. And for example, classes split into subclasses. And also one of my favorite topics, class imbalance and fairness, how to deal with the data distributions evolve to the point that the distribution becomes imbalanced. How to deal with the fact that previously seen minority classes may become majority ones and vice versa. How to deal with situations when minority classes disappear and we don't have any new examples coming for them. And also how to move this beyond vision, how to extend it to time series, tabular data, text, audio, etc. So as I mentioned, this is just like a short talk to kind of highlight you a couple of interesting questions and how data stream mining continual learning actually should be researched as a one big silo of adaptive systems and how to look forward to creating more holistic, more adaptive continual learning systems. And I think I'm out of time. So thank you so much for your attention. And I would love to answer any questions that you may have.
Thank you very much, Bartek, for the wonderful presentation. So I'll start by asking if there are any questions from the audience. Okay, let's check. Okay, no questions from the chat. I guess I have a question about the latest work that you presented. I was curious about the evaluation protocol that you used and also about your view on forward transfer
Mhm.
when used in combination with the backward transfer, because it looks like in many continual learning papers, there is only mention of backward transfer. And my question is if you think there is value in data streams for tracking both, and what is the interpretation of it if and even if it can be exploited during learning.
Mhm. So this, I mean, Roberto, excellent, very loaded question. So maybe try me to like just, divide it into chunks and try to answer it and see if I covered everything. So maybe I'm going to start with the backward versus forward transfer. I think this is extremely important topic. And one of my big issues with a lot of papers that are being published nowadays is they do not track a holistic evaluation of all of those metrics. As I say, some papers track only backward left transfer, some papers track only forward transfer. But you think about this, we need to get a better control over the flow of our machine learning algorithm. Because when new data arrives, how to deal with this? Maybe we should have a selective forward transfer when we revisit past tasks, do some kind of a task similarity, and instead of trying to say, oh, entire network should contribute to learning for the new task, maybe we can identify a subnetwork or the most similar tasks that should be elevated to speed up the training and the adaptation of new task. This is like a big situation that we're trying to deal with because one of the collaborators that I have is working sensor networks in Africa, and we're trying to detect poachers in Africa. So basically situations when they drive into national parks, shoot an elephant, drive out. This is a situation when you're going to have these anomalies, atypical situations, etc. And the speed of adaptation is crucial. So you have this big neural network that's been trained on sounds of like I cannot even imagine the biodiversity in African countries. But you cannot just like when you have a new sound, it may be human, it may be a car, you don't really know. You cannot start pulling from everything. So we're trying to do this kind of like a tiny subnetworks and very quick matching based on like any kind of a KL divergence laws, etc. Which subnetwork should be pulled in to be initialization parameters for the new task. So this I think on the forward transfer, but on the backward transfer, also, maybe we can mix it with experience replay, identify similarity backwards, and then revisit those old tasks, mixing a little bit of new instances, hoping they're gonna help us a better adaptation. Most of the papers do not do this explicitly. They do it implicitly, saying, "Oh, look, we did this, and our backward transfer, the accuracy in all tasks bumped." But I think there's a lack of basically like a systematic approach how to truly measure it and how to truly disentangle the fact that our network changes parameters, and does the drop or gain accuracy comes from the transfer or just the random solution that the network just converts in at the current point. So I would say this is a very fascinating but very demanding direction for the future. And I remember you said some question about the evaluation protocol, if you could refresh my memory on that one.
Yes, so for the last work, I was curious on what was actually measured and
Mhm.
how it was measured. Yes, how do you get to the final scores? I probably missed that. Yes, so if there was an explicit division into tasks or
Mhm.
concepts or
So we use the standard popular continual learning framework with basically class incremental setup. So the tasks were independent classes. We measured accuracy per task, final accuracy, forgetting per task, and final average forgetting. Plus, on top of that, we measured the number of samples required for updating the buffer. So basically, how much are you asking with our selective method versus how much a full relearning would require samples, which you can imagine the other one is easy, it's just the size of the buffer, basically. So this is like our upper bound. We measure the GFLOPs and we measure the update time per epoch, depending on both of those methods. So those were the main metrics we measured. Basically, we didn't do a bigger study at this point of backward forward transfer, focus on accuracies, forgetting rates per task or at the end, and the free performance metrics. But basically, it follows traditional continual learning 10, 20, 40 tasks and standard data sets, Cypher, ImageNet, etc., split into those tasks with our injection of concept drifts, 2 or 4 concept drifts per data set.
Thank you very much. That addresses my question.
Thank you so much.
Any other question from the audience? Okay, so thank you once again. It was really nice to see.
Thank you so much. And thank you so much for the invitation. It was a
Your work on
pleasure.
this frontier topic.
Thank you. And good luck with the rest of the workshop and hope to see you soon in person.